Okay, good morning and welcome to this next lecture on sound and structural vibration. We are looking at this topic of cylindrical shell waves coupling to internal fluid. Okay. So far we have looked at how shell flexural waves behave. So we have to now bring the fluid aspect in it. Okay. So suppose we have a rigid walled cylindrical shell. Okay, wall does not move, it is a rigid pipe kind of. Okay. Then the solution to the cylindrical wave equation has this form. Let us say Pmn r phi z, time term I assume is some amplitude cos or sine n phi, okay. Then Jn, the same order, k n m r into r e to the power of minus j k z z. Okay. So this is the solution for the mnth mode. Okay. Normally it will be a summation over m and n. Okay. Now how are the k's related? The k square or k z square plus k n m r whole squared is equal to k squared. Right. So now you are aware of how the wave numbers add, right. So I have at a given frequency I have a k, this is equal to omega square by c square. So at a given frequency in the shell I have a k, the shell goes up to infinity, I have a k in some direction that shall be equal to the kz, okay, in the z direction versus k r n m in the radial direction. So that is what this equation is saying. Okay. So now ideally we are looking at the rigid walled, okay, to understand, okay, the cut-ons, the cylindrical acoustic cut-ons. Okay. So now at the wall the displacement is 0, okay, the normal displacement is 0, which means at the radial in the radial direction r equal to a, we will have Jn, the Bessel function first kind nth order derivative at r equal to a shall be 0. Okay. Now because Bessel function is like a transcendental function, there are several kr a values that will satisfy this condition, even for a single. So let me draw the Bessel function. So I will just draw the 0 or the J0, right. J0 behaves like this. It is like a decaying sinusoid. Okay. So this is J at 0. So you can see its derivative goes to 0 here, its derivative goes to 0 here, its derivative goes to 0 here, goes to 0 here, goes to 0 here, goes to 0 here. Okay. So this is kind of the radial direction. Okay, you can put a this kind of the radial direction. So this is how the circumference of the shell should go. Okay. So you are trying to find values of Kr such that Kra lands here, Kra lands here, Kra lands here, Kra lands here. Why? That is where the J0 derivative goes to 0. So for a single n there are several values of m where this happens. So if I just draw a table now, m values are in this here, then n values 0, n0, m 0, 1, 2, 3, 4, etc. Okay, so the m values. For n equal to 0, the first derivative, first time derivative goes to 0 is for m value 0. Okay, and the value of the wave number is 0. The value of the wave number is 0. So that means Kra is 0. So here are Kra values. So Kr into a values. Okay, so you, because for J0 you get a derivative 0 right at 0 value. Okay, so the next value where derivative goes to 0 is 3.83. Okay, that is the Kr into a value. Kra is equal to 3.83. So if a is known, you can find out the actual wave number value. Then the next time it goes to 0 at 7.02. These are tabulated. Okay, so these are Bessel functions tabulated. Then for n equal to 1, the first fellow is at 1.84, second is 5.33, third is 8.53, 11.71, etc. n equal to 2, it is 3.05, 6.71, etc. Okay, so these are the cut-on frequency, or where Jn dash goes to 0. Okay, so now what we have is we have kz square plus a particular knm r whole squared is equal to k squared. Okay, now kz is of course equal to square root of k square minus knm r whole squared. This is figured out from the table on the left. Okay, so when kz goes to 0, that is my cut-on. Kz goes to 0, that is my cut-on condition. Okay, which means my k or omega by c is equal to k n m over r. Okay, so omega is that cut-on frequency. Omega is the cut-on frequency. So if we put it in non-dimensional form, okay, so we have omega a, so I have to do omega a by c, this is speed of sound, is k n m r into a, okay, but my non-dimensional frequency is what, omega a by c l dash, okay. So I had to put c l dash, then I put c l dash, okay. So what is it, omega a by c l dash, which is my omega, is equal to k n m r a, these are the tabulated values, into c by c l dash, okay. So this is the speed of sound, sonic speed in that particular medium, is the speed of longitudinal wave, okay, in that medium, in the structure, okay. So that is the cut-on non-dimensional frequency now. So once I figure out KNMRA from this particular table on the left, the way to figure out the cut-on frequency in terms of the standard non-dimensional number that we have been using for frequency is you multiply that by C on top, divide by CL dash on the bottom, okay. So now these are the, this is how I figure out my cut-on frequency value. I have figured out the cut-on frequencies for the structure. We have figured out after cut-on how these wave numbers behave, okay. So below omega equal to 1 they stay low, close to 1 they start to rise suddenly, okay. So now how does this acoustic wave number behave, okay. Suppose we have, let me do one thing, I need to put some labels, okay. So this is the omega axis, and let us say this will be n0, this will be n equal to 1, this will be say n equal to 2, and this is kz a beta to the power half. Now based on our table, let us look at where the kz's cut on, okay. So for n equal to 0 and m equal to 0, based on the table earlier, k00 r a was 0, okay, which means kr00 is equal to 0, which implies at the same time that the non-dimensional frequency omega is 0, okay. Then for n equal to 1 and m equal to 0, okay, let us say for steel and air, okay, combination, my omega 10 will be 1.84 into C, which is 340 divided by 5000. This is speed of sound in the air, this is longitudinal wave speed in the medium, okay. This is about 0.125. Similarly, if we do for aluminum and air, okay, the omega 10 is equal to 1.84, okay. Similar values, 340 by 5000, about 0.12. If we do steel and water, then we have 1.84 into 1500 by 5000, which is 0.55. Okay. If we do n equal to 2 and m equal to 0, still water, then we have from the table KRA is 3.05, 1500 by 5000 is equal to 0.915, and if we look at n equal to 0 and m equal to 1, from the table KRA value is 3.83 into 1500 by 5000 is equal to 1.14. Okay. Now circumferentially, how do these nm values appear as? So if I have this circle, n0 and m0 looks like this. Okay. n1 m0, how does it look like? N equal to 1 denotes the nodal diameter. Okay. Then m equal to 0 is nodal circle. So no nodal circles. So we have a nodal, one nodal diameter, so plus and minus. How does n1 and m1 look like? So we have one diameter, one circle. Okay. So we'll have plus minus plus minus. Lastly, we'll look at n equal to 3 and m equal to 2. Okay. So m2 gives me 1, 2, and 3 will be 1, 2 and 3. So let's say we'll do minus plus minus plus minus plus plus minus plus minus plus minus minus plus minus plus minus plus. Okay. And we can plot these cut-ons along the frequency axis. So we get Kz on the y axis and the frequency value here. Okay. So we have Kz, which is equal to square root of k square minus k n m or mn r whole squared. Okay. So the k00, it cuts on straight from omega equal to 0, so it goes like this straight away. So next we have the n1 m0, okay, where the KRA value is 1.84. Okay, so KRA value is, this is 1, 0 and this is 1.84. Okay, this is the KRA value. Okay. Then we have 2, 0 sequentially, 2, 0. So this will asymptotically go to plane wave. So this value was 3.05. the next value is 3.83, the next value is 4.2. So 3.83 is 0, 1 and 4.2 is 3, 0, 3, 0. There will be a corresponding omega value from here. Okay. So these are the KRA values. Okay. Now for the structure, the flexural behavior in the circumferential direction looks like this. This is for n equal to 0, is a breathing mode where the shell radially expands and contracts. Okay. And for n equal to 1, we will have a cosine theta type variation. So the shell profile oscillates back and forth, left to right. Okay, so it moves back and forth, left to right. This is a nominal circle. It moves, oscillates back and forth. Then the n equal to 2 is easier to see. It's the ovaling mode. So if we take this as a nominal circle and it ovals, so it in one part it goes like this, in the other half it goes like this. So it ovals. This is n equal to 2, then equal to 1. Okay. And let me say that coupling between fluid and shell is circumferential order based. Circumferential order based, that means n based. So the n of the structure couples with the n of the fluid. Okay. So that means when the structural wave number of a particular n comes close or crosses to a fluid wave number of the same n, same circumferential order, then coupling is good. Coupling is good. So if we now plot both the pictures, so what we are now going to do is plot both pictures. Okay, so this is my ring frequency. Okay, so let me plot a few structural cut-ons. The first one starts at 0, stays low, n equal to 0, and then starts to rise rapidly. Okay, and then it starts to bend like this. The next one maybe cuts on here and then also stays low. Okay, and somewhere it starts to rise and it behaves like this. The third one starts maybe here and does some meandering, etc., etc. Okay. Now let us say that my plane wave line is going like this. Let's say plane wave line. The plane wave line goes like this. Okay. Or let me do one thing for clarity. Let me leave it. Let me say it's it has a higher angle, okay, does not matter. Okay. Now my acoustic cut-ons, they will rise vertical, the acoustic cut-ons will rise vertically straight and then they will go. Based on the structure and fluid properties, the number will be decided. Based on the thickness of the shell wave numbers will be decided, etc. Okay. So these fluid cut-ons rise vertically, and as I said, the coupling is N based. So a particular N, okay, of a structure, let us say, can intersect with a certain set of N's, okay, a certain set of N's. Maybe somewhere here there is a, maybe somewhere here there. So a particular structural wave number carrying a certain N with it will go and intersect all those cut-ons, fluid cut-ons which have the same N, okay, and that is when coupling occurs. Okay, strong. Let me say one more thing here, that we are plotting uncoupled waves. Okay, so that means what? We have looked at structure as though it is in vacuum and plotted its waves. We have looked at fluid and as though the structure is rigid and plotted its waves. Okay. This helps us get a picture, this helps us get an idea of what is happening. However, actual waves are coupled. So in actuality, when both are present, this is not the picture. So I would like you to understand that. However, this picture of this way of plotting the uncoupled waves together gives us a physical feel for what is happening. Okay, so we will continue with that. So what I was saying was that a particular N structural flexural wave cuts on and remains low in its value till omega equal to 1, and therefore along its path it intersects all fluid cut-ons with the same N, with the same N. And this intersection is a kind of coincidence where the structural wave, if it is vibrating, will communicate with the fluid, or if there is a lot of sound in the fluid, it will communicate with the structure. Okay. So these intersections are very important. Okay. Now for certain dimensions of, let us say, fluid pipes, it so happens that a large number of coincidences happened around here. It is possible based on the structural material, the fluid material and the diameters and so forth. It is possible that you have a lot of coincidences. So it has been observed that transmission loss drops. Okay. In thin walled cylindrical shells, in thin walled cylindrical shells. Around ring frequency. that is omega equal to 1. Okay. So now this is the picture in general. Okay. Now let me just give you a flavor of external radiation, just a flavor for external radiation. Now you have structural waves that are staying low, okay, and then they rise very suddenly, okay, and then they become dominantly flexural and so forth. So here this is what is happening. Okay. Now my non-dimensional wave number is omega a by Cl dash, whereas my wave number, acoustic wave number k is omega by C, and therefore in terms of this capital omega, it's omega into Cl dash by C, right. Or if I want k is equal to omega by C, so omega into Cl dash, omega into Cl dash divided by A. Okay. Or if I want Ka, then we will leave it as omega Cl dash by C on the omega axis. Okay. So this based on the relative values of Cl dash, the longitudinal speed in the material and the speed of sound in the fluid, the acoustic wave number line could lie here or it could lie here. Could lie here like this. Okay. So in terms of external radiation, it is scenario 1. Okay. Scenario 1 is that the waves cut on supersonic, right. Why? Because Kz happens to be below K. Okay. Then around omega 1, the Kz rises and it becomes greater than K, okay, subsonic. And then much later, you will reach the critical frequency you will reach the critical frequency of the shell material considered as a flat plate. Okay. There the flexure again drops. Okay. There the flexure drops and Kz becomes less than K, so that the shell is again efficient. Okay. The shell starts off as an efficient radiator, loses its efficiency and again becomes efficient. That is one scenario. Just a minute before I change the page, let me put the labels. So this could be say n equal to 0, this could be n equal to 1, this is let us say omega axis, this is Kz A beta to the power half. Similarly this is omega, let us say this is n0, n1, n2, and this is kZA beta. The other scenario is, it is possible that the ring frequency is above your coincidence frequency omega c, where you consider the shell as a flat shell material as a flat plate. Okay. Then right from cut-on, the waves or the flexural waves are supersonic. Okay. So, this is for external radiation. I will close the lecture here, we are running out of time, we will continue next class. Thank you.